in the last 20 years, since, imaging has become a big interest of the Field Museum, we did about 19,000 images in 20 years. I was able to do 13 and a half, so getting close to that number in much less than 20 years, in fact, in just a few weeks' time.
Hello, and let's talk about bugs, computer vision, science, and how those things are coming together to unlock brand new possibilities for researchers. Today, we are joined by Elizabeth Postema of the Field Museum of Natural History in Chicago, and we're going to be diving into a project that she, along with many other researchers, created recently. It's super cool, and I am happy to have the chance to present it to everybody. To get us started, Elizabeth, would you like to introduce yourself?
Absolutely. Thank you both for the mini introductions. But just to introduce myself personally, I'm Elizabeth Postema. I'm a postdoctoral researcher here in Chicago at the Field Museum. I've been here about 2 years. I graduated with my PhD in animal behavior from UC Davis, and I'm really obsessed with two things. One of them is insects, and hopefully by the end of this, I can convince you that insects are worth your time and are very cool. And the second thing is the ecology and evolution of color traits. And so those two things come together and mean that I need a lot of data because insects are a very diverse group. And so AI is really helping me kind of get through those data points.
All right. Well, thank you so much for joining us. To get us started, I have a picture over here that I think it's safe to say, like, my favorite picture that I've seen this quarter, at least, this past year. Can you tell us what's happening in this photo?
Absolutely. So, well, first, I just wanted to ask a question for the crowd. If anyone has actually been to the Field Museum in Chicago before, I don't know, you can do your little hand raise icon or put it in chat. Any hand raises? Have none of you guys been to the Field Museum? Okay, a few. Keith, yes. Okay. No, would love to. Okay, great. Yeah, come on by. I'm there up on the third floor. But yeah, so the Field Museum and other natural history museums hold really immense collections of natural history objects and specimens in particular. And so this is actually a photo of the Smithsonian that I totally just took off Google because it's a really great demonstration of how insects are stored. We have these like big collection boxes, and they're usually separated into little trays, typically by taxonomic order. So you might have one species or one genus per tray. And often it's also separated by location. So where in the world these things were collected. And as Patrick and Jackson both alluded to, some of these collections are huge. So at the Field Museum, first of all, we actually don't know the exact number of how much stuff we have, just because we have such a huge collection. But we probably think, at least for pinned insects, this is somewhere around 8 or 9 million. And it's closer to 12 million if you account for all of our wet specimens. So things that we store in jars of alcohol. And so this massive amount of data is kind of both a blessing and a curse. It's a blessing because there's a lot you can learn about the natural world from preserved specimens. Some of these are decades or even hundreds of years old. One of the oldest ones we have in the collection was actually collected by Charles Darwin himself. It has his signature on it. So there's a lot of cool stuff in there. And if you're an evolutionary ecologist like me, I'm really interested in exactly what you're seeing on the screen, which is a whole bunch of different shapes, a lot of different sizes, and most importantly for me, all sorts of different colors. And museum specimens are nice, insects in particular, because most of them are structurally colored. And so what that means is that the color patterns on their outside of their body are not from a pigment. It doesn't degrade over time. So some of those like blue morphos you see in the bottom of the picture, those may be decades old and they look exactly how they would have looked, when they were collected. And so that's really handy for me. Um, and so historically, the way you would image and digitize these collections would be to pull out a drawer, bring it up to the imaging lab, take each individual specimen off from the unit tray or from the drawer, and then you'd pull the labels that are carefully arranged on the pin, and those labels contain a lot of the metadata. So things like where it was collected, who it was collected by, when it was collected, and some other identifying information. More recently, you might find a QR code on there so we can keep track of individuals. But all of that information is useful. And so normally you take those off, transcribe it, put it in a museum database. We use something called EMU. It's very low tech relative to the kind of stuff you guys are probably used to working with. I think it hasn't changed since it was developed. It looks like Windows like in the 90s. It's pretty crazy. I don't have any photos of it, but just believe me, it's pretty funny. And so you do that part and then you take a photo of it. Usually you'd get a dorsal photograph, maybe the underside if there's some important identifying features. And why do you guys think it might be useful to have images and metadata digitally available? Any ideas?
We see Zach mentioned quicker than going to the drawer.
Yes, absolutely. And so especially quicker if you are a researcher who lives in, say, Germany. We actually just had a visiting researcher from Berlin. It's definitely a lot quicker than him flying all the way here and pulling out a drawer. And so one thing is to make collaborations across countries, across institutions much easier. A huge, benefit of these collections is it allows people to reference the taxonomic identity. So if you're collecting a new species or what you think might be a new species, you may want to check the existing species that are already here to make sure, oh, these have characteristics that are similar or not. Maybe I do have a new species. So that's one thing. We get image requests all the time. We just got a new collections manager, and that's like one of the main things she's dealing with. So that's one thing. Just logistically, for curation purposes, it's really useful to have those things digitally available. And then Charlotte mentioned to quickly search for features, colors. So yeah, once you have images, you start to be able to do morphological analyses. So you can start to get things like color, size, shape, all of that kind of stuff. And then I'll fill in one other thing that I think is really pertinent now is if we know what was there when it was collected in a particular location, it's really helpful for things like conservation. So we have definitely endangered and recently extinct insects in our collection, and we can look there and say, how has their population changed over time? Have they moved to different ranges? Have they stayed in the same place? What's going on? So there's a lot of things you can learn from museum collections, and the easier those data are to access, the easier it is to do that kind of research. So yeah, that's kind of the background of collections and why digitizing is important.
Yeah, before we move on, could you also perhaps talk a little bit about if we take a step back,
Sure.
like why would we want to quickly search for different features and colors across like a broad set of different specimens? Were there sort of like any kind of challenges to doing research that you could talk about that you had previously?
Yeah, absolutely. So the thing with studying morphological traits in something like insects is that you have a bunch of different levels of variation. So on one hand, a single species may be really polymorphic, and that just means it might look a lot of different ways. You might have redder ones, greener ones, so on and so forth. Next level up, at the family level, so a little bit higher up that taxonomic chain, you're also going to have variation, between one kind of beetle and another closely related beetle. You go one more up to something like order, so all butterflies or all beetles, for example, that's suddenly you get these compounding layers of variation. And ultimately, evolutionary ecologists often have to choose what level of complexity they want to get at. So if you're looking across an entire order and you want to know, hey, like, when did this blue color pattern evolve, for example? Normally, you would basically have to say, well, I'm not going to get all of the data from everyone. So you have to choose maybe like one image for like, 100 representative families. So you're not really getting a very fine scaled, detailed analysis. You're just getting the very top layer of that variation. The other way you could do it is just go, okay, I want to know how this trait evolved in this single species. And then you look at all of the specimens for that species to quantify variation that way. So there's kind of a trade-off in how broad you can go versus how much you can characterize variation on that lower level. And I guess even taking a step back, like, why do I care about color patterns in the first place? Maybe that's what Patrick was really getting at, is that color is really important in ecological terms. It plays a lot of roles. And so it's one of the main ways that insects communicate with predators. So think of things like camouflage, or if you've ever seen a ladybug, it's bright red and black. It's saying, I'm toxic, don't eat me. And there's a lot of other different crazy things like mimicking broken sticks or bird poop or leaves. So there's a lot of different strategies that insects use to avoid getting eaten. And, color, shape, morphology, all of those things are important. Some of the other things that color does is thermoregulation. So for, cold-blooded things like insects, being dark is actually probably pretty good if you're in a colder environment because it allows you to heat up faster. And for us, we can throw on a coat. For them, they really rely on those physiological processes. And so there's all these different axes that color is kind of interfacing with, physiology, communication, sometimes sexual communication, sometimes predator defense. And so being able to know how those traits have evolved over time gives us a really cool insight into whether there are bigger patterns that shape those systems. So hopefully that makes sense.
Awesome. Yeah. Well, let's start taking a look at the solution that you and all of these other researchers at the Field Museum and other organizations worked on. I have a few slides here with some images that you shared with me ahead of time. From my perspective, it feels like there's like a couple different things you've solved with computer vision. One being, understanding the traits, the attributes of the specimens, and then there's going to be another thing about transcribing data. I think here, this is maybe like part of the first kind of solution. Could you just introduce the kind of DrawerDissect, the software that you created, and then what we're seeing here?
Yeah, absolutely. So just to reel it back even a little bit further, I got involved with this project just as a new curator of insects came in. So this is Bruno de Medeiros. He's basically my advisor for this project. And he, joined the Field Museum just a year ahead of me and pretty immediately secured funds to get a really cool imaging rig called the Gigamacro. And so what this helps in terms of imaging, that's sort of one pipeline that needs to be optimized. is now we don't have to take every single specimen out to image, which takes a very long time. Instead, we can basically plop our drawer or a set of trays down on a platform, and the camera will move automatically to boundaries that we've set. And so for that, you do, the corners of where all your specimens are, and it takes photos at each station. It also focal stacks, so you get the z-axis. Everything is nice and in focus. We have this big as heck telecentric lens on it, and that just means that there's no warping or parallax. And so you end up with this like hilariously large photo. It's about 7 or 8 gigabytes, the TIFF form of that. So that's like the size of a small like Steam indie game, basically. Um, uh, and it's great because you have everything in one place. You have, potentially hundreds of specimens, all really high quality, high resolution. You can zoom in and it's as if you took a photo of just, of a single specimen. But of course, that doesn't actually solve our problem, because ending up with a huge image with a bunch of stuff on it is cool, but it doesn't actually get you to the specimen level. And for that, that's really where I came in and where Roboflow comes in, because all of the kind of computer vision models like detection and segmentation are exactly what you need to break down that whole drawer image into individual trays. So you can actually see right here, this is what I mean by a unit tray. And you can see at the top there, we've actually added these special labels that pop up when we're imaging, and then they fold back down when we put them back into the tray. And so, for example, these are a stick-spotted tiger beetle. This family is really beautiful and iridescent. And these are actually in the Nearctic regions. So that just means that they've been collected probably in the United States. So these guys are running around. Many of you have probably walked past them before. And so one of the philosophies of DrawerDissect is to basically break down steps like as finely as possible. And so I don't just go from drawer straight to specimen. We go down to unit tray first because it has a lot of information that are going to apply to all of the specimens. And then you can see here, this object detection model, Bug Finder, aptly named, is doing exactly what it sounds like it will do. So it's finding all of the insects in a tray, putting a bounding box around it, and numbering those specimens, which is useful for later if we want to associate it with metadata or with a QR code or things like that. And then I didn't want to just stop there. Like, just a single dorsal image is great, but pretty much any kind of analysis of features of an insect is going to involve painstakingly outlining the body or different anatomical features on the insect. And so segmentation, at this point, everyone on their phone has this, where you just, press press on an object and it outlines it for you. And so same principle here. We're using a segmentation model, bug masker. I know I'm really creative with these names, to get sort of the main chunk of the body, ignoring the legs and antenna for now, just because of how variably positioned they are. So I'm just getting that main head, thorax, abdomen. And this is trained on, gosh, at this point, probably thousands of different insects. We started initially just with tiger beetles because that's what we, started imaging. But at this point, we've expanded to a bunch of different species. I think maybe there's a photo showing segmentation on different things coming up, but
Yeah, probably. Yeah. Before we look at that, maybe this is a good point to, I think like here, this might be related to what's happening after, or perhaps this is answering the question of why segment the bodies.
yeah.
I love charts. I don't know what's happening in this chart, but could you,
Well,
is this connected? Could you let us know about that?
yeah. So one of the first things that's useful about segmentation is you can create masks of the body and basically say, hey, like, beetles are roughly oval shaped. If you want to get the length and the width measurements, you can just do that because you can essentially just say, hey, what's the longest line between 2 points along this contour? And then for the width, usually it's pretty accurate to just say, hey, what's, the longest perpendicular line to that initial length measurement. And I actually verified this. So me and one of my interns took some old school like calipers and went in and measured probably like 70 or 80 tiger beetles by hand, which took a very long time. Roboflow combined with DrawerDissect does this very fast by comparison. And so the charts you're looking at here are just that validation. So on the x-axis, you have the manual length in millimeters, and on the y-axis, you have the length output by DrawerDissect. And so if you look at that line of correlation, it's very tight. You can see we have some really big ones. Those are Manticora. They're really cool. I'll see if I can find an image of them for you guys later. But more importantly, that R-squared value, so how good the fit of those two measurements is very high. It's almost a 1-to-1. And so we're getting very accurate measurements of thousands of specimens at once when it would normally take, hours to do this kind of work.
Beautiful. All right. And actually, so I see we had a question from Charlotte about some of the insects being pinned over their descriptions and kind of stuff like that. That's a little bit related to actually maybe the next slide, I'll say. We can, of course, return to that question more in depth later.
Sure.
But here, what we're looking at, I think this is part of, in my mind, what seems to be kind of like the second problem, which is related to the pins, the labels. I see there's numbers, there's printed text. Sometimes you're dealing with handwritten text, which at this moment I'm choosing to believe this is Charles Darwin's handwriting until somebody proves me wrong. Could you let us know, what are we seeing here? What is this solution that you created with these AI models that we're seeing here?
Absolutely. Yeah. So as you guys kind of saw in that tray image that I showed you already, there's a lot of information in these images, basically at every level. And so as much as possible, I'm trying to like squeeze as much data, whether it's text or features of the specimen or, other things like that, how many specimens are in a tray, as much information as I possibly can from these images. And so here you're seeing the pre-processing that I do to get text information specifically. And so, as I mentioned, a convention of insect drawers is that they have labels that describe the species or whatever the lowest taxonomic unit it's described to. So in this case, you're seeing Cicindela formosa, and on the right, you're seeing this Eo moth, this Automeris eo. And then for the Field Museum, more specifically, we also have things like the broad biogeographic region it was collected. So again, here, this is NEA, this is Nearctic. We also have things from, NEO, like the Neotropics. And then on the bottom left, or rather, the left side in the purple is a barcode that we've generated to keep track of individual trays. So ultimately, at this point, from the Field Museum perspective, all we actually need is the barcode because the other information is already associated. But on the right, you can see that I want other people to be able to use this too, that may have much less standardized data. So in this case, this is like a handwritten label, not by Charles Darwin. I'm sorry to say, Patrick. This was actually by a really cool collaborator of mine, Lucy Goriani. She's a graduate student at Ohio State who we actually just met at an entomology conference. I did a talk describing this work, and she came up to me and was like, I have 17 drawers of moths. Can we do this? Like, can I do this with these moths? I was like, sure. So she, took her 17 drawers in a car and came to the Field Museum from Columbus. And we imaged all of them, and she's actually finishing up her dissertation with those images and that research right now. But that's a bit of a tangent, but sorry. Not Charles Darwin, but a very cool researcher anyways. And so at this point, this is a pretty simple detection model saying, hey, find these features of text that you might see, in a drawer in a unit tray. And then I end up using large language models with specific prompts to transcribe that information. I find it's just easier to give large language models as little noise as possible, because if I gave them the entire tray, that I'm sure it would just pick up all sorts of random stuff. It might think that the insect legs are letters, like stuff like that. So as much as you can be like, this is a single image of text, and I also kind of up the contrast, put it in black and white, do some pre-processing to make it really, really easy. And then that returns in, a nicely formatted spreadsheet, basically. And that's a nice feature of DrawerDissect is all of the spreadsheet outputs at the final step get merged together into a single, well, actually into 3 data sheets that are compatible with EMU, our databasing system. And so they can be uploaded, associated with the images, and so on.
All right. That's, I couldn't have explained the need to first use one model to isolate text and then pass it to like an OCR or language model better. I'm going to be using some of that phrasing in the future.
Yeah.
There's one more chart here. I love this chart as well, even though I don't know what's going on. Could you let us know what we're seeing here?
Sure. Yeah. So right here is basically a demonstration of the fun things you can do with thousands of specimens worth of data. And so just for hopefully tapping into some like intro bio class knowledge, if anyone remembers a thing called Bergmann's rule, it's a broad biological principle. I know some of us were more recently in, undergrad bio than others, if at all. But Bergmann's rule is essentially this observation that things tend to increase in size as they move away from the equator. So as latitude increases, there's this sort of general observation that you see things increase in size. This has a lot to do with thermodynamics. So, reducing your surface area to volume ratio helps you keep warm. And then the opposite for warmer climates. But it's really just a principle. It's an observation that people have tried to kind of validate or disprove over time. And so one cool thing you can do with huge data sets like this is actually look at those like basic like 101 kind of rules or observation that you learn in class and say, hey, is this actually true? And so that's something, I was able to actually do here. And so if you look at the x-axis there, it's going to be latitude. So this is absolute latitude. So going from 0 to 60 or 0 to negative 60 if you're in the southern hemisphere. And then on the left is just a logarithmically transformed body size, just because there's a lot of variation in body size. So it accounts for that kind of non-normal data. And then on the top in the italics, you can see the names of different genera. So Cicindela is like clearly one we have a lot of. You can see a ton of data points. And then going down from there. So these were some of our, like most common genera that we have in the tiger beetle collection. And so you can actually see in 4 of the genera, there is quite strong and actually statistically significant support for this idea that body size increases with latitude. So that's really cool. This is pretty quick and dirty, so there's some bias in terms of like, probably you're going to see more stronger correlations and things where you have more observations. But if you look at these other ones, it's not across the board. So Lophyra, Neocolorus, Omus, all of the ones with the black lines are actually pretty weak associations. And Ellipsoptera, you may actually start to see a trend of the opposite direction, and Hypatia as well. So I'm not going to go too far into the like crazy, biology and evolutionary reasons for this. All this is to say is that once you have a lot of data, there's a lot you can do with it.
I am convinced that I will someday see a Postema rule in some textbook going forward now, just on this short conversation. All right. This is one other. Oh, actually, so before we keep talking about maybe some results of surveys and then what we see here, something that perhaps we haven't covered yet is how many specimens have you analyzed? Like how many kind of drawers or sort of what's the scope of the sort of like the results that you've seen from having this DrawerDissect solution? And I think that might help us kind of lead into this slides conversation, I'm hoping.
No, I think it totally will. So just in tiger beetles alone, it's 44 drawers. And so as far as insects go, that's a pretty small family. It was kind of a nice, like bite-sized group to work with. They're also really beautiful and have a lot of interesting color patterns and, features of their natural history. And so we ended up being able to image 44 drawers in about 2 or 3 weeks, which is insane. Like that is not the usual rate at all. And so for context, those 44 drawers were about 3,500 specimens. Again, like 3,500 in a couple weeks with some really cool interns I had through the Women in Science program at the field. And then since then, I think we've gotten to, imaging on and off something like 150 drawers. And so that's getting up to, gosh, whatever, 150 times like probably 200 or 300 per drawer, let's say. So if anyone's really quick with math, that's getting, into the, tens of thousands of specimens. And just for reference, in the last 20 years, since, imaging has become a big interest of the Field Museum, we did about 19,000 images in 20 years. I was able to do 13 and a half, so getting close to that number in much less than 20 years, in fact, in just a few weeks' time. And so you can see how the two-pronged approach, so both high throughput imaging and high throughput image processing, you start to get like truly crazy levels of data and images like really fast.
Awesome. All right, man. I'm just still kind of thinking about this number of 20 years versus 2, 3 weeks, a couple weeks. All right. With that said, what are we looking at on this slide? I think we had spoken once previously, and you had told me a couple stories about identification, identifying different specimens. Is this related to that story that you had told me once upon a time?
Yes, that is directly related. Yeah, so one thing about DrawerDissect is that the results of it, you have these nicely masked out specimens where the only information on the image is information pertinent to that specimen. And so I'm sure some of you guys have worked with classification models before. They tend to get really tripped up by things like shortcut learning. So they'll cue into stuff that isn't actually relevant to try and give you the category that it thinks it belongs to. And so the less information you can give, or rather the more specific information you can give, the better your classification models are going to be. And so for our case, I think museum specimens are going to become a huge repository for training species identification models, or, identification models across entire families or orders even. And so we actually tried that out. So we used these masked version of images. And so this is for the entire genus Cicindela. And we had, I went in and found this group at the end of the cabinet, this tray of Cicindela that had not been identified to species. Like it was unknown in our collection. And so I went through and, used traditional methods, a dichotomous key. I looked through and did my identifications. And you can see that in the table those are my results under human identification. And then we trained a model. So we actually didn't use Roboflow for this. I forget the exact model architecture we were using, but it's up on a Hugging Face page associated with the preprint. So you can go check that out if you want. And basically found that our classification model did a really good job. So the things with the bold outline are things that it got right, at least in line with my identifications. And there were really only two where it didn't misidentify per se. It just said, I don't know. It just said, I'm not going to answer because I don't have a good idea of what this is. And one of them I actually don't fault it too much for, because it was this kind of obscure Japanese species that even I had trouble knowing if I got it exactly to the right subspecies. So I'm not surprised. We didn't have any of it in our collection, so it was not trained on this. So obviously it's not going to like find the right thing if we don't even have it in our collection. The other one, the Silvicola, was just a true kind of false negative. And so not perfect, but pretty good. So you can see how valuable these kinds of images, especially once you get thousands of them to train really good ID models.
Yeah, that reminds me of some other sort of like industrial use cases I've seen where you have people doing these, how should I say it, like subjective tasks where they need to use their eyeballs and minds to look at some data and then produce like a judgment.
Yeah.
And if you can, give that person a little bit of assistance, I think it reduces a lot of the like mental fatigue for those people where they don't have to do all of the identification and all the judgment calls on their own. It's nice to have a friend who's like, well, hey, I looked at the images and I kind of got it most of the way there. You might want to still review this and take a look at it, but at least we reduced some of that mental fatigue along the way.
Yeah, I think that probably a good goal that I can see for species ID models is not to replace taxonomists, because a lot of things you need to actually physically handle the specimen. But I think it gets through a lot of the common species that it would probably, not take that long for a human person to identify it anyways, but because there's so much of it, it takes a while. And so for these things like this, ocelota, there's a bunch of these. They're really common in our collection. It's nice to be able to just go through, an unsorted sample and be able to say, okay, we know what all of those are, and then get to the things like the Transbicalica japonensis that we're like, we might actually have to go in and like look at some more defined features.
I think that we had one more slide about like kind of going into some of the behind the scenes stuff that's happening. Elizabeth, you had mentioned having a live demo that you might be able to share. Do you still want to do that? If so, I can stop sharing my screen.
Sure, I can just do like a really quick little kind of just showing like what it actually looks like in practice to deploy these. Okay, so let me share my video. Okay, so here's the main structure. Now, disclaimer, I had no coding or programming experience whatsoever before starting this project. So if it looks really messy and clunky and taped together, forgive me, it works. And that's the most that an ecologist needs. And it does work. So essentially what you can see here is we've got it set up where there's sort of a main processing script, and then all of my configurations are in this YAML file. And so that includes things like API keys, model versions, all of that kind of stuff, as well as the prompts for text transcription. And all of those are editable. You can go in there and mess with them, mess with some of the memory settings if you want to do parallel processing. There's a lot of features, and you can dig into that more if you look at the GitHub too. And so the main structure here is that if you go into this drawers, you can see that there's a place for unsorted. And so that's where you would put that initial full drawer image. And then once you set it to run, you can actually see I've already sneakily done this in advance. It's already done the first step in the process, which is to resize that image because it's really big. I probably can't even open it on this computer, or my computer will like break. I'm just on my like crummy laptop right now. And it automatically puts it in this folder and then makes a ton of different places for where all of those outputs of the pipeline are going to live. So if we go here, we have that full-size image, and then hopefully this resized image I can actually open and kind of show you a little bit more of, yeah. So this is kind of what the full-size image looks like. Obviously it's compressed, so the resolution isn't as good, but this is like the start of the pipeline here. And so there's a couple nice features, just like quality of life stuff that I've built in over time. One is that you can do different steps in different sequences. So you can combine them into unique workflows or just do one, or you could just do Python process images and all. And so if you wanted to just go all the way down the line, process everything, you would input that. In this case, I'd probably get to something like find trays, and then crop trays. So let's see if that works here. And then if I had multiple different drawers, I could put this flag here and say, only do, this FMNH Sysindelidae 3457. At the moment, I just have one test image in there, but you can just run things on individual drawers. And you can, combine workflows for single drawers. You can rerun stuff. So if you've updated your model and you don't want to just go back through and delete everything, you can say, hey, rerun this drawer with these steps with this new model that I've put in the config file. So let's see if this works. Since it's a live demo, it probably won't, but that's fine. And so it's thinking. And yeah, so you can see, aha, error, excellent. That's fine. I think probably because I didn't put a version number in this. I didn't. Okay, so here you can kind of like sneakily look behind the scenes and see all of the different model endpoints for all your Roboflow people. This should look really familiar. You can put in the confidence, overlap, all of the stuff that you guys naturally output. Okay, so let's go ahead and let's use version. I'll use version 8. Okay, let's try that again.
We are very familiar with the demo gods not smiling with us during our weekly sessions like this. Totally normal.
And so you can already see it's loading those API keys. It's found 16 trays in this image in about 4 seconds. And then now it's going ahead and resizing those images and cropping them. And so the resizing step is usually the one that takes the longest, especially on my computer. But if we were to go in here and look in this coordinates tab, you can now see that it's found a bunch of trays and given me the coordinates for all of those trays. And then it scales it back up to that original image to crop them out into individual trays. So let's see if we can actually see it doing that. This step usually takes a while because, again, it's taking that full image. It would be faster on my work computer, but here we are.
Yeah.
You can kind of see the broad logic. And so if you were to run all of these steps, it would basically go through and do each of these with the output of one thing being the input for another. So I think that's all I really had to show for now.
Beautiful.
I don't know, it's probably going to take a while to crop these trays out.
Yeah, we have a couple other things we could look at, and maybe if we want to, we might be able to come back and take a peek later on.
Yes.
Yeah, let me share my screen again. I actually have a few slides that might be related to some additional questions that we got from the audience as well. Now for like kind of reference, and actually, so there was a question from Luis, about like for your body size, length, width measurements, do you get those by calibrating to a certain ratio each time? Or is it a preset from the distance, camera rig, something like that? This is actually related to one of my questions as well, which is, so this is the camera that you mentioned, the tray, one of them. And I also wanted to ask about these little these little doggies that we have down here. And I think this might be also related to Luis's question as well. From a photography background, this does look like some kind of control. I see a couple different colors to handle things like white balance, making sure you get the colors rendered the same way each time. But yeah, could you tell us a little bit about capturing imagery, making sure that things are calibrated? How do you handle that?
Yeah, so in terms of size for the chat question, it's really easy for us. We have a telecentric lens, and what that means is that through some kind of unknown physics and light magic that I cannot describe to you, but that others might be able to, no matter how far the camera away is from the subject or how close, it has the same field of view. So it's a set distance and basically a set pixel to millimeter ratio. And so that's really nice. For the big telecentric lens we use, it's about 105 pixels per millimeter. So that's something you can just incorporate automatically into your measurements. But if you don't have that, in like a metadata file or whatever, it just returns the pixel values, and then you can figure out your millimeter to pixel ratio later through things like ImageJ. But most places will have some kind of scale bar or some kind of ratio for their whole drawer imaging. And for the little color standard, that's exactly right. So we take this whole drawer into Lightroom and calibrate it color-wise using this color standard. We've actually switched to a little nano one, which is much nicer because it has a smaller footprint. And the doggies and cute stickers, those aren't just for fun. Those are a weird quirk of the Gigamacro Flow software that we use to stitch those massive images together. One thing about drawers and trays that they have a lot of blank space, and stitching programs like PTGUI is what we use, really hates like vast, indistinct white backgrounds, and it will like infinitely vortex things together in improbable combinations and like crash your computer. And so we put these like filler objects both into the trays and on any place where there's like regular or blank space to help the stitching process. We're trying to figure out a way to get around that just because it's kind of annoying and it makes the picture look kind of funny, but this is our best solution for that right now.
No, please keep the dogs that protect your computer from crashing. That sounds very important. I'll take a quick moment here too, just while we're talking about measurements and calibration for this audience question. Really quickly, in some other situations where perhaps you don't have a magical camera lens that always gives you the same output, if you're working with some other cameras, there's a couple things that people tend to worry about. One is going to be like lens distortion, and then making sure that you have the same measurements each time. I do think there's a lot of industries or a lot of use cases where people can make sure they have the same measurement each time using some kind of reference like on screen. And I actually see that there's already a little bit here. Maybe we don't see it completely because you don't need it in this situation. And then when it comes to lens distortion, you'll see a lot of people use those like checkerboard. It looks like a chess set. Maybe it even is. There's these calibration mats that you get, and then you take an image using that. And then actually, even in Roboflow, we have some blocks in workflows. They're used for creating a rule to always apply the same lens distortion correction afterwards. With that, I was going to move on. Quick time check. We're going a little bit over time today. Elizabeth, are you okay? Do you need to stop at the hour, or is it okay if we go a little bit over? Great, cool. Nice. I think this might be one of my final slides that we had today, and you sort of mentioned it earlier, but my question for you was like, are you a machine learning expert? Did you have a lot of experience creating custom computer vision models before this? Tell me about that journey of, you know, postdoctoral researcher working on bugs to you're an expert in computer vision now.
Well, thank you. Yeah, so No, to answer your question, I had done zero AI or Python for that matter. The most coding I had done as a graduate student was in R, doing very simple analysis of predation. I was basically a field ecologist. So what I was doing in grad school was basically the opposite of what I do now. It was running around in the woods, like, measuring plants, looking at predation, all of that stuff. And I found that ultimately, I wanted to get some more quantitative skills in my toolbox as I start applying for things like faculty positions. And so this was a really great opportunity. And I felt like, I learned pretty quick. I can just figure this out as I go. And I ran into this idea of AI, and I talked to my advisor about it. And so I started pretty small with things like fast AI and like starting to figure out PyTorch and stuff. Um, the question I had was like, how do I even labels? Like, how do you actually like label something or just like the bare bones basics of like, how do you train a model? Like, I have no idea what is even going on. And so I Googled like how to annotate a vision model, and Roboflow. Clearly your SEO is very good because Roboflow and maybe a few other things popped up. And this to me was the most intuitive interface. So it was very familiar to me as someone who has done like digital art, and I've worked with some image data before. It just had things organized in a way that I could understand as someone who is pretty new to it. And I feel like once you get that foothold and once you have a very clear idea of what the steps need to be, it makes it a lot easier to ramp up and, learn as you go. And so that's kind of what happened in my case. And, 5 years ago, if you told me I was like writing, Python scripts that link AI models together, I'd be like, what are you talking about? But here I am.
Cool. All right. And my other question here is about kind of like annotation, labeling, and then about some of your data sets. I guess I have a couple questions that are all getting lumped together. You mentioned having thousands of labeled images. I think some of those are also public if other people want to use your data sets and train models on their own, right?
Absolutely. So one of my main goals as a researcher and as someone in a museum is like, we want people to use these tools. It's not just, we're not trying to hoard this tech and just process our awesome collection. So, uh, I've actually ended up, and this kind of answers some Zach's earlier question about like other institutions. So I've been working pretty directly with two people, one at the American Natural History Museum and one at the Australian National Insect Collection, who have had whole drawer images for like almost a decade, a little more than a decade, because a lot of museums got this drawer imaging rigs, these drawer imaging tech, kind of things, and then didn't really know what to do with the output because computer vision was not as accessible in 2012. And also see ya to folks who are leaving. Thanks for I realize I'm going a little over time. But essentially, yeah, these are publicly available tools. I think even if you just have a free Roboflow account, you can do this. You have some inferences. And so I think for, other institutions, this is something they can use to start processing those backlogs for sure.
Beautiful. All right. Yeah. I think we have a couple more things that we could go through, and then we might be able to wrap it up. Um, there's perhaps this one kind of final behind the scenes look. I think this is related to the whole pipeline. Some of this we already covered though earlier in the presentation about just taking some detections, cropping it, things like that, post-processing, feeding it into a language model to get back some of the results we saw. So maybe we'll skip over that for today. Um, a sort of like final question for you, Elizabeth, is like people who are interested in this topic, in DrawerDissect, what are the kind of actions that you hope they could take, or if they're interested in learning more, where should they go?
Yeah, so the first thing is to read the preprint that I have out on this work. It's actually currently in review, so stay tuned for the fully published version at some point. hopefully in the near future, but you never know how these things go. But at least for now, you can kind of go into the nitty gritty of how the pipeline works, why we think it's impactful, and how people can use it. And then there's also a GitHub associated with it, and I can drop that link into the chat if people are interested. Oh, you already have them already. Thank you, Jessica. Yeah, and we didn't really get to the transcription part of this as much. What I failed to say is that once you get down to the specimen image, and I think maybe Charlotte was asking about this earlier, in a lot of cases, you can partially see where it was collected from that top label in the image. And so again, in the effort of, good but not perfect, just trying to squeeze as much as you can out of all the images you're getting, I came up with this multi-step process. You can kind of see it in that location transcription module in the middle of this image. Basically, what I end up doing is flipping that image on its side. Usually specimens are vertical, and so you want text reading horizontal. And you can kind of make out like it's like 3 miles northwest of somewhere, Garfield something. And as someone who's worked now in collections for 2 years, I can pretty much immediately tell you where that is just from the context clues and sort of the common abbreviations. And so I figured I could teach a large language model to do that as well. So the first step is basically it takes the verbatim text, just what exact letters it can see. And then I give it some context about museum abbreviation conventions. I'm hoping to actually give it later a reference library of collections that I've already gotten to give it a better idea. And then I kind of have it go back and validate. So given the verbatim text and your initial assessment of where this is from, is this a reasonable guess? So I kind of have it check its homework. And ultimately, the last thing I'll say sort of on this is that all of these steps, also including labor of prepping the drawers for imaging, merging the data, everything, it ends up at about 41 seconds per specimen on a decent Windows computer, which is pretty amazing for all the stuff you get out of it.
Stupendous. Yeah, that's a really impressive result. Yeah, this 3 miles northwest of Rifle, Garfield, Colorado, a county, I guess, Colorado, USA. That's amazing. That's super cool. All right, so that I think wraps up the material that we prepared. My quick little break here is always if you're watching a recorded version of this somewhere on YouTube and you want to join a live session in the future, please head on over to roboflow.com/webinar. So if you have any other additional questions, feel free to drop those in the chat. Elizabeth, I do want to go back to, I'd say, let me take a quick look here. Oh yeah, please, yeah, go for it if you already found one.
It's a great question. Regarding masking from the 2D image, when looking at digital specimen photos in an online database, would this process still work? And yes. So basically all you would have to do is instead of starting at the whole drawer image, you would start by making your own drawer folder, having a place to put specimens, and then doing those masking steps. And so I have support for specimen only masking. And I've used that actually for a few different things. One of them was for some old like UV images of butterflies that I was working on for a previous project. I actually ended up masking all of those so I could get, color and size information. And then the other thing I've been using that for, and just a more general, like just cool collaboration I want to shout out, is with Kelton Welch over at Digitize, which is an awesome nonprofit that works with farms across America to do biodiversity surveys. And so he has essentially a version of what I'm doing, but for wet specimens. And so they collect these specimens in alcohol vials, he dumps them out, takes an image of all of them together, and he's, figuring out some workflows for how to process them. And so I actually just shared the weights from my segmentation model with him so that he could use that to help segment out, insects from the background. And so this is ultimately, if you check out the co-authors list, this is a very collaborative project. I'm working with people who all have basically the same problem. And, everyone here who has, worked in industry knows that there's this issue of we need to process a lot of stuff. Well, what if we take a big picture of it? Okay, well, now we have to, figure out how to parse the picture. And that's the general workflow, I've been working through.
I have actually, I want to go back to Charlotte's question earlier. This is actually relevant to something I was working on recently as well, where um, the question was about, do you also detect body parts other than the main body, or do the legs and the letters underneath look similar for a good detection? I mentioned this because the other day I was working on a model to look, it's like drone footage of a parking lot, and there are these parking stall numbers, and then I was detecting the parking stall and then passing that to OCR because I wanted to be able to like read all the different parking stall numbers, and then like the asphalt next to the number is a little bit lighter, and then when I crop, the OCR model kept thinking the asphalt was a 1, and I was like, okay, so I need to crop in a little bit so I stop getting that extra little asphalt there that thinks it's like I always add another 1 in there. So maybe this is about body parts, it's about OCR and improving those results.
Totally. So the one thing with specimens is that they're really variably positioned. And my goal in the imaging step is to do as little fussing with them as possible. I want, DrawerDissect to be able to take everything kind of as it is, whatever skew it's at, whatever angle, so on and so forth, and just grab everything. And for the masking step, at the moment, I don't have something to segment the legs. I think for more specific anatomical features, like if you want to get like antenna length or I don't know, the length of the tarsus, you're just going to need more specialized models that I haven't developed. I'm working on color features. Legs are often not even visible for a lot of these specimens, especially the bigger ones. And so I've kind of focused on like what is the most detailed chunk I can get without getting into territory where all of these extensions and holes, basically, so non-continuous portions, how can I avoid that as much as possible? Now, I would love to go back now with some of these and segment out certain features. I think one place to do that in our Lepidoptera, so moths and butterflies, is to get like specific wings. For example, like maybe you want to get just the length of the forewing. And that's something that, other people have certainly been working on. In terms of the descriptions, yeah, I think that's part of what mixes things up. The other thing I'll mention is that pale or transparent things are still like tricky. And so, if it's a really light moth or beetle or whatever on a really light background, if it's trying to find edges, it's going to potentially have trouble doing that. So the way I solve for that is by overloading it with things that it's bad at. So I'll find stuff in the collection that are very pale, and I will weight the model with those things that it's not that great at. And so you can kind of do targeted improvements. Or say I'm introducing a new taxon, for example, that looks very different than the stuff it's already trained on. You just need to add a lot of that until it performs similarly.
Nice. Yeah. I wonder if there's also some, even just on the image capture, like even before you go to the model, some things you would be able to do there. Just, I'm thinking about like factories where they want to train AI to be able to see like gas leaks. They don't use, traditional imagery. They use imagery that is able to see the gas leak, and then it's very specialized imagery. It doesn't look like what the human eye would usually see. And then they train computer vision models specifically on that specialized imagery. So maybe perhaps that's something to investigate. Or I'm not sure if you've already tried doing that, changing contrast, stuff like that.
Yeah, I mean, I do a lot of augmentations in my models, so there's definitely contrast and grayscale and all of that kind of stuff, which I think has improved performance on some of those lighter edges.
we've taken up a lot of your time today already, Elizabeth. This was a fantastic session. I loved hearing about the story and the work that you and everybody else at the Field Museum and some other organizations have been doing to create this really awesome solution for understanding this collection of insect specimens and then speeding up some of your research. If anybody has some remaining questions, I see there was one from Luis about dealing with some like underwater distortion. If you have some questions, feel free to send me an email. It's just patrick@roboflow.com. Um,
Oh,
yeah. Oh,
desired. I just threw it in the chat. So get in touch if you're curious about bugs or chaining models together or what have you.
wonderful. All right. Thank you so much for our audience today, and thank you so much, Elizabeth, for joining. Maybe we can wrap things up there today.
It was my pleasure. I guess I did want to share one more really quick thing.
Please, please.
Is that, let's see, it did it. So just to prove
Oh yeah, sorry, I'd completely forgot to go back to your I will stop sharing. Yes.
cropped in all of the trays. I'll try and open one. So there you go. So it was able to find this tray and crop it all out. Anyways, just wanted to show you that, and it outputs all of them in this sort of nicely numbered order.
Yay. Cool. And then that's like, sorry, that's like the maybe first step, right? Because you start off with a giant image and one drawer, and then within the drawers there are multiple trays, right? And then I'm imagining there's like 20 more steps after that.
The full list is on the GitHub.
Cool. All right. You okay, well, maybe we'll end there. Check out the GitHub. Yes.
The Field Museum.
Yes, please. All right. Thank you so much.